Welcome back, everybody. We're now in Chapter 3, Section 4 in College Algebra. We're taking a look at library of functions today, as well as piecewise defined functions. So what are the library of functions? Library of functions, what we can see down here underneath at the bottom of the screen, are just a series of functions that it's very good to know about and having a solid working knowledge of what the basic graphs look like in their names, in because we use these a lot in algebra. And then in one of our subsequent videos, we'll take a look at every other function then can be based off, or a lot of other functions can be based off these, and then we just move them around. We make them taller, we make them shorter, we stretch them to we stretch them out right and left. We move them to the right, we move them to the left. And there's a variety of different things that we can do with these. So starting off, what we want to do is take a look, see if we determine whether the function is even or odd, and then or neither, and state if it's symmetric both with respect to the y-axis, the origin, or neither. Find the intercepts, graph it, state the domain and range, and just a variety of different items. So let's take a look at these one at a time. So on number 1, we've got the constant function. So on this one, f of x equals b if b is just some real number. So when we take a look at this graph, well, let's see. Let's let b be this value. If you remember back in slope-intercept form, b is our y-intercept. So let's let b be the value where we cross the y-axis. And then notice if b is just a number, it doesn't matter what my x is. My y always has to be the same thing. So my y can be here, and here, and here, and here. I can go back off to the left. But it doesn't matter what the x value is, my y value is the same. That's why we call this a constant function. So on this particular function, we can take a look at it. We say, well, this is symmetric about the y-axis. And so let's see, we've got symmetry about the y-axis. That means it's also going to be an even function. If we think about our domain, it doesn't matter what value I choose for x, I always have a corresponding y value. So I have no restrictions, so I'm going from all real numbers, so negative infinity to positive infinity. And my range here, the only value that I have for my range is whatever this value of b is. And my range is what are my y values that I get back out of the function. And so there is our constant function. Let's take a look at number 2. Number 2 is the identity function. So f of x equal to x. Get a little cleaned up just a little bit here. So when we take a look at it this way, okay, so here's our graph. So as I take a look at the identity, let's see, 1, 2, 3, 4, let's kind of mark some things out here. The identity function is whatever my input is, my output's got to be the same thing. So if my input is, -4, my output is also -4. My input's -3, my output's also -3. -2, I'm also -2. -1, also -1. 0, 0. At 1, I'm 1. At 2, I'm 2, etc. So what we end up with is we just have a line that goes to the origin with a slope of 1. As we take a look at this one, is this even, odd? Where is the symmetry? Let me go ahead and draw this graph a little bit nicer because I do want to go through the origin there. There we go. Maybe I should have used a straight hand tool on that or a line tool, but we get the idea here. And this point over here, okay, just highlighted there is at 1, 1. Okay, if I would reflect it over the y-axis, I'd be over at -1, 1. And if I reflect that over the x-axis, I'm at -1, -1. So I'm symmetrical over, if I combine those, then I'm symmetrical over the origin. So I have symmetric about the origin. And if we're symmetric about the origin, that means we're an odd function. Again, one of the things to note is what is the exponent here on x, and it's 1. I don't have anything listed, so that means that it is an odd function overall. And let's see, my domain, There's no restrictions I have to be concerned about. I don't have a square root. I'm not divided by anything. So my domain is all real numbers. In my range here, if I take a look at how high and low this graph goes, it goes down to negative infinity, goes up to positive infinity, and so this is all real numbers as well. Let's then scroll down through here. Let's take a look at number 3. So number 3 is the square function. So we say f of x equals the square of our input. So we've also called this a quadratic previously. And if we would have done our t-chart on this one, -2, -1, 0, 1, 2, we're just squaring each of these items. So the square of -2 is +4, square of -1 is +1, square of 0 is 0, square of 1 is 1, square of 2 is 4. And so at -2 we're 4, at a +2 we're 4, -1 we're 1, +1 we're 1, and then we're down at 0. So we end up with this nice U-shaped graph, and as we take a look at that, looks like we're symmetrical then about the y-axis. So we have symmetry about the y-axis. Notice that our exponent here is even, and the only thing we have is that exponent. I could have put some other number out here. It would be +0. I'll just leave that alone. Don't want to muddy the waters up here. So it's an even function. And let's see. Our domain on this one. We're allowed to put anything in that we want for x. Now our range here, we only go as low as 0, and then we keep going up towards infinity. Okay, so if I take a look at my y-axis, I only go as low as 0, and then I keep going up both directions, kind of right and left there. As I go a little bit to the right as I go up, a little bit to the left as I go up, but overall I'm going up. So I'm going from 0 to positive infinity. Since I am available to be at 0, then I have to go ahead and put this with the bracket in the interval notation. Okay. I think one of the things our directions also asked us to do was to find the intercepts on these, and I apologize for not doing that on these first couple items. On number 1, we've got just a y-intercept at b. We don't have any other intercepts. So the y-intercept is b, and the x-intercept, there is none. On number 2, our x-intercept was 0, and our y-intercept was also 0. We just sell that from the graph. And over here on number 3, our x-intercept is 0, looking at the graph, and our y-intercept is also 0. Take a look at number 4 here. We got the cube function. So now instead of doing f of x being x squared like we did in number 3, now in number 4 here we've got the cube function. So f of x is x cubed. So I can take a look at x and then f of x, which says cube everything. So do our standard kind of items for our t-chart, -2, -1, 0, 1, and 2. Then we multiply it by itself 3 times. So when x is -2, I've got -2 times -2, which is +4, times another -2, which now is -8. When I multiply -1 by itself, I get -1 times -1 is +1, multiplied by another -1 is -1. 0 is just going to be 0. 1 multiplied by itself any number of times is 1. 2 multiplied by itself 3 times is also going to be 8. Let's see, it was that -2 is -8. So at 2, we've got 2 times 2 is 4, times another 2 is 8. So as we take a look at our graph here, so at -2, I'm -8, -1, -1, 0, 0, 1, 1, and then 1, 8. So our graph looks like this. And when we take a look at this particular graph, we can see that from the graph, it looks like we're symmetrical about the origin. We could check that algebraically. We could say, what is f of -x? Well, that would be -x cubed. which is then the negative of x cubed, which is the negative of f of x. And so if f of negative x is the negative of f of x, that is the algebraic definition of what it means to be an odd function. Graphically, we could say, okay, take any point, reflect it over the y-axis, then reflect it over the x-axis. If both of those in sequence hold true, then graphically we say that we are an odd function. So a couple other items that we want to point out here then. Let's see, our x-intercept was 0. Our y-intercept is also 0. For our domain, looks like, again, like our other functions here, we don't have any square roots. We don't have any division with a fraction. So any number we want to use is available. So it's all real numbers. We can write that in, we can write that in interval notation as negative infinity to positive infinity. Should have had the parentheses, or parentheses around that instead of the curly braces. For our range, if we take a look at our graph here, looks like we're going down to negative infinity, back up to positive infinity, and everything in between gets used. So we have all real numbers for that as well. Then my infinity symbol. Sometimes my infinity symbols look a little strange in through there, and I apologize for that. This is how they get every once in a while. Okay, so we've got our, what do we have so far? We've got our constant, our identity, our square function, our cubic function. Let's see what else we have in here. Then we have our square root function. So we can say f of x is the square root of x. So if, again, we take a look at our t-chart, anything that's negative would not make sense. If I try to take the square root of -2, I'm asking what multiplied by itself. The square root is what multiplied by itself equals that item. Okay, and so nothing quite fits in here, because if I multiply a negative times a negative, I end up with positive. Multiply a positive by a positive, we also get a positive. So anything with a square root just would not make sense, which means immediately we're restricting our domain to be the numbers between 0 and infinity. I can use 0, okay, because the square root of 0 is 0, square root of 1 is 1. Square root of 2, I don't know exactly. Square root of 3, I don't know exactly. The square root of 4, I know is 2. So typically when we graph these, we go ahead and we skip along a little bit, and we say, okay, well, what are the things that I do know about? Let's move this down here a little bit. So my next perfect square I know is 9, so that would be 3. Next one would be 16, and that would be 4. So we kind of, not quite cheat, but we know where we're going with it, so we can shift our function. So let's see, we've got 1, 2, 3, and then let's see, 1, 2, 3, 4, 5, 6, 7, 8. We'll go up to 9 here. So there's 9. So let's see, at 0 we're 0, 1 we're 1, at 4, 1, 2, 3, 4, 4 we're 2, and at 9 we're 3. So we look something like this. So this is going to end up being our square root function. This is not symmetrical about the y-axis, because I have some items in quadrant 1, but nothing in either quadrant 2 or 3. And it's not symmetrical about the origin, because, again, I would have to be able to reflect against the y-axis, then again against the x. Nothing's down over there, so it's not symmetrical about any of those. So symmetry would be none. So no symmetry, so this is neither even or odd. And let me go back up through here. I think we forgot about this one. On number 4, oh, we did say it was an odd function. I thought we had left that one out. Okay. So in our square root function, other items we're looking for, so we need our range. So our range looks like our y values start at 0, and then they go up from there. So our, in this case, our domain and range end up being the same things. Our x-intercept is 0, and our y-intercept, in this case, is also 0. So we did the square function, the square root function. We did the cube function. Now let's do the cube root function. So let's say f of x equals now the third root of x. So what we're looking for then, if I do my x and f of x, is what multiplied by itself 3 times gives me what's underneath the radical sign. So if I just kind of pop over here to the side and do some quick calculations. 0 times 0 times 0 is 0. 1 cubed, 1 times 1 times 1 is 1. 2 cubed, 2 times 2 is 4, times 2 is 8. Let's see, 3 cubed, 3 times 3 is 9, times 3 is 27. So if I do the cube root of 0, that was 3. So what multiplied by itself 3 times was 0. Cube root of 1, what multiplied by itself 3 times was 1, was 1. What's the cube root of 8? So that was 2, because it was 2 cubed, got us 8, 2 times 2 times 2. And we see the same pattern developing here. That would have been 3. Interesting enough, we could take these in a negative direction. Negative 1 times negative 1 times negative 1 is negative 1. Negative 2 times negative 2 times negative 2 would be negative 8. And if you see a pattern developing here, from the bottom here, we had positive 3 to the power of 3 is 27. Negative 3 to the power of 3 is negative 27. So not quite symmetry there, but fairly reasonable. So as we take a look at these other values, if I do the cube root of negative 1, it's negative 1. Cube root of negative 8 is negative 2. Cube root of negative 27 is negative 3. So what we can do is we can take a look at some of these items, and I could say, all right, well, the cube root of negative 8, I know was negative 2. Cube root of negative 1 was negative 1. Cube root of 0 was 0. Cube root of 1 was 1. Cube root of 8 is 2. I could do 27 in here and come up with 3. And let's see what this graph looks like then. Let's see, there's negative 1, negative 2, 3, 4, 5, 6, 7, 8. There's negative 8. And positive 1, 2, 3, 4, 5, 6, 7, 8. And at, let's see, at negative 8, we were at negative 2. Negative 1, we're negative 1. 0 is 0. 1 was 1, and 8 was 2. So we end up looking like this. Which, if we could rotate the screen, it's somewhat similar then to the cubic function. Kind of rotated off to the side, maybe flipped over, but that's the same general idea that we have there. And so on this function, let's see, what do we have if I plug in negative x? Then I end up with the cube root of negative x. And the cube root of a negative is going to be negative, so I can just pull that out front, because negative times negative times negative is going to be negative. So that really is the negative of f of x. So if f of negative x equals negative f of x, by definition, that is an odd function. That means we are also symmetrical about the origin. Okay. What was our domain and range? So our domain here, we do have a root, but it's a cube root. And anytime we have odd roots, we are allowed to have negatives. Negatives underneath odd indices are okay. So we're ended up with negative infinity out to infinity. And our range here, we're slowly getting, going higher and slowly getting lower, but we do keep doing that. So we end up with all real numbers again. And let's see, where are we missing here? We're missing our x-intercept is 0, and our y-intercept in this case is also 0. Okay? So that is almost all our functions here. So that was number 6. I think we had 9 of these overall. So let's see. So number 7, I want to talk about the reciprocal function. Clean up my writing here. Reminds me of trying to sign my name on one of the credit card readers. Sometimes the electronic items here aren't quite as precise as if we were just writing paper pencil. But we adjust and adapt, and we figure out what we need to do. So the reciprocal function is 1 over x. Let's see. So if we do some values here, let's see, negative 2, negative 1, 0, 1, and 2. Reciprocal of negative 2 is negative 1/2. Reciprocal of negative 1 is 1. reciprocal of 0. Well, that would be undefined because we can't do 1 over 0. At 1, we're 1, and at 2, we're 1/2. Interesting on this one, we end up with a bunch of fractions here. What if we add some other values? What if I get close to 1? So if I input some values here, what if my x is 1/2? The reciprocal of 1/2 is 2. If I get a little closer and say 1/4, then my reciprocal is 4. I wanted to do that so we could see what's taking place here. So we're not defining that x equals 0, but at 1, let's see, at 1 we're 1, at 2 we're 1/2, but at 1/2 we're 2, and at 1/4 we're 4. So the closer I get to 0 from the positive side, the higher I go. And if I do my reciprocals, I get close to 0 as I go out to the right, and then it reverses going the other direction. It'll look like so. Okay. So on this one, let's see. As we take a look at what we end up with, on number 7, if I go ahead and take a look at, well, what happens if I plug in negative x? And I get 1 over negative x, which is the same as the negative of 1 over x. So f of negative x is the negative of f of x. So by definition, this is an odd function. And we have symmetry about the origin on this one. As far as our domain, looks like anything we have except 0 will work because I have a denominator. I'm dividing by this value, so x is not allowed to be 0. So in my domain, I could just say it that way. X is not allowed to be 0. Or I could phrase it as in the set builder notation. I can say all x such that x is not allowed to be 0. Or I could phrase this as I'm going from negative infinity up to 0. Combine that with 0 out to infinity. And if I use the parentheses here, that means I'm not including 0. And in my range, my range is going to be the same thing. I'm just not including 0, only it's the y's are not that. So I could say my range are all my y's, such that y is not allowed to be 0. Or again, I could say, just like we had above, negative infinity to 0, combined with 0 out to positive infinity. So a variety of different ways we can go ahead and state that. But that is our reciprocal function. As far as our x and y intercepts, see, we did not cross the x-axis anywhere. And the y-intercept, we didn't cross the y-axis anywhere. So it's not going to happen. Last item, number 8. I'm sorry, not the last number. We got 2 more items. The absolute value function. So the absolute value f of x equals absolute value of x. So absolute value function, remember absolute value from other algebra classes is the distance that we are away from 0. So if I have just a quick review here, 1, 2, 3, and then negative 1, 2, and negative 3. If I'm at this point here, how far is that away from 0? That distance is 1. If I'm at this point here, negative 1, how far am I away from 0? The distance is still 1. It just happens to be left of 0 as opposed to the right side of 0. So when we do distance, we're not concerned about are we on the right or are we on the left. We just want to know how far are we in that regard. So if we do our graphs here, our t-chart, at a negative 2, how far is negative 2 away from 0? It's 2 away from 0. How far is negative 1 away? It's 1 away. 0 is no places away. 1 is 1 away from 0, and 2 is 2 places away from 0. So when we take a look at our graph here, at negative 3, I would have been at 3. And negative 2 is 2. Negative 1 is 1. 0 is 0. 1 is 1. 2 is 2. 3 is 3. So that right side looks like part of our identity function. The left side is pretty close here. And so as we take a look at this one, we do have some symmetry we can see that visually about the y-axis. That means then this is an even function. Likewise, I could have said, okay, f of negative x is the absolute value of negative x. The negative doesn't matter, so that's just absolute value of x, which is the same as f of x. So since my negative got swallowed up in the function, that is indeed the algebraic definition of even. Let's see, we got our domain. Domain, anything that we want to use for x is okay. So that's all real numbers. And my range looks like I got as low as 0, and then I kept getting higher and higher. So I'm going from 0 to infinity. Let's see, my x-intercept is the same as my y-intercept, which is 0. So we cross at 0, 0. Now we're at our last function. What we have is what's called the greatest integer function. So f of x equals int x. That's one way to write greatest integer function. This is sometimes called the floor function also. Meaning then that we want the greatest integer less than or equal to x. So we want the greatest integer. So how big can we get that's less than or equal to? Okay. So how close can we get without going over? This is the function I like to describe as the price is right function. Remember, Price is Right television game show. How close can you get to the actual retail price without going over? And the closest one wins, and you can win the prize if the price is right. Please help control the pet population. Have your pet spayed and neutered. So the old show there and all the different things that memory brings back. So as we take a look at this one, this is kind of an interesting item here. I'm going to go ahead and start off with the graph. So as we take a look at that, if I am at 0, what's the as close as we can get to 0 without going past 0? Well, I can go ahead and be at 0. Okay? And so if I want the integer function of 0, the closest I can get to 0 without going over is 0. What's the closest I can get to 0.5 without going past 0.5? So if I went close to 0.5 without going beyond 0.5, but I got to use an integer. And my integers, maybe we should put this off to the side here, just to refresh our memory. Our integers are the whole numbers and their opposites. So they're 0, 1, 2, 3, etc., and -1, -2, -3, etc. So there's no fractions, no decimals. So how close can I get to 0? Think about it on a number line. Excuse me, if there's a number line. So how close can I get to 0.5 with an integer without going past 0.5? Closest I can get here is 0. Because if I go to 1, then I'm past it. So the closest I can get is 0. What's the integer function of 0.9? So how close can I get to 0.9 out here without going past 0.9? So I can't skip over it. So the closest integer I can get to, again, is 0. So notice on this one, this is an odd function. We never round on this one. Sometimes people, I guess let me rephrase that, we're not rounding up in this case. So people would say, oh, this is a rounding function, so up to 0.5 round up. In this case, no, we don't round up. We go ahead and we still leave it at the value. So from 0 to 1, I'm still going to be at 0. Now notice here, I did put a open dot there because my integer, how close can I get to 1 with an integer without going past 1? I actually can be 1. So I'm going to have this open circle down here at 1, 0, but a closed circle at 1, 1 because 1, 1 is an acceptable value. 1, 0 is not. How close can I get to, say, 1.3 without going past it? Okay. So if I do an example over here, how close can I get to 1.3 without going past it? Just 1. How close can I get to 1.8 without going past it? Again, just 1. So if I go to 2, then I'm past 1.8. So I'm going to end up with this little line here, and we're going to end up doing something of this sort all the way through. This is our greatest integer function, and so if we carry this along the way as far as this pattern, it's going to keep looking like this. So another thing that this function is called sometimes, okay, is a step function. Because it could look like a set of stairs. You know, if I would connect these, okay, then I have a set of stairs that I can go ahead and walk up. Okay, and so that is our step function. How close can we get without going over? So let's take a look at the other parts and pieces here as far as what we want. Okay. On this one, it does not appear as though we have any symmetry here, so there's no symmetry. Okay. For my domain, looks like I can choose any number I want. So my domain is negative infinity to positive infinity. My range, though, notice my definition was the greatest integer less than or equal to that particular value. So my range here are only integers. Okay. So another way I could list that out, so I could say dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. Okay? So that would be my range. So only the integer values along the way. Okay? You might also see that another way to write that is a z with an extra bar on that diagonal piece. So that would be another way to write the integers. Okay? And let's see, my intercepts here, my x-intercept. X-intercept is, what do we have? Between 0 and 1. So I actually have a range of values here. And then my y-intercept is at 0. So if we zoom in over here, okay, my y-intercept, where do I cross the y-axis? I cross the y-axis here. I touch the y-axis here with the open dot, but the open dot means I don't actually touch it there. I'm just getting super close. Okay. All right, so what did we just do? We just did our library of functions. So the library of functions overall, oops, I'm trying to get my, there we go, trying to get the slide up here. Library of functions are these functions. These are the functions that overall we like to know about because we use these consistently in algebra. And so if we know the basic look of it, then we're okay as far as what we're going to do with other pieces. Because what we want to take a look at next is analyzing piecewise functions. Okay? So what is a piecewise function? Let's go ahead and scroll on down here. A piecewise defined function is a function that's defined in pieces. What do we, kind of roundabout way. But this function here, f of x, well, it's -2 when x is less than 0, and it's the square root of x when x is greater than or equal to 0. So my function then is defined in two distinct pieces. I have a piece here, and I have a piece here. So I'm splitting up my, my function into different parts. Okay, so on letter A, let's see what we can do here. So letter A says find f of -4, f of 0, and f of +4. So if I want f of -4, I need to figure out which of these two pieces am I referencing. Am I referencing the top part when I'm less than 0, or the bottom part when I'm bigger than or equal to 0? Well, -4 is on the left side of 0, so I want to go ahead and use this top part. So I want -2 times -4, so that's going to end up being +8. If I want f of 0, well, which one of these am I going to use? F of 0 is going to end up being when I'm equal to 0, so greater than or equal to, so that's going to end up being the square root here. So the square root of 0 is going to be 0. And then what's the value of the function at 4? So 4 is bigger than 0, so I want this piece. So I want the square root of 4 which is 2. So figuring out when I use the function notation, what's the value of the function, I need to take a look at what is the specific area that I'm in. Am I going to be in this region, or am I going to be in that other region? Letter B, find the domain of f. So in piecewise functions, what we have to do is we have to take a look at this section over here, the pieces. When are we defined? So we're defined when we're less than 0, and we're defined when we're greater than or equal to 0. Let's see, if here's 0, less than 0 is everything out over here, greater than or equal to is out over here, and so we end up using everything. So my domain in this case is going to end up being all real numbers. Now, one of the things that could have been different, if I would have had some other pieces in here, then it would have changed some things, but we'll leave that for another story. So there's B. Let's take a look at letter C. Locate any intercepts. So to find the x-intercepts, remember what we do? We let the y value equal to 0. So let's see, if I let y equals 0, then I get 0 equals, well, I'm either going to be 2x, or I'm going to be the square root of x. Depends on which one we're taking a look at. So when we do the y-intercepts, we have to go ahead and we'll take a look at the x-intercepts, have to take a look at both scenarios. So if I go ahead and solve this for x, I'm going to divide both sides by -2, so that x equals 0. And over here, if I solve this, I'm going to square both sides, and x equals 0. So regardless, x is going to be 0. So when is x 0? That's officially down here. So that's the official part of the graph when we're taking a look at the x-intercepts. Going to cross the x-axis at 0. Now, the other thing we want to do is locate the y-intercept. So we locate the y-intercept. We let x equal 0. Well, x is 0 only at this bottom piece. So then I can say, okay, what is f of 0? So that's going to be the square root of 0, which is then going to be 0. Now, if we want to go ahead and graph this, let's take a look at what we will have. Let's go ahead and put a few points out here. So let's see, our function is defined in pieces. So we are -2x if x is on the left side of 0. So if I was trying to plot some points, if I was going to do a t-chart here, x and f of x, if I want to be left of 0, okay, if I put 0 in, -2x would be 0, but we're not using that one, so we kind of ignore that. At -1, so I'm going to the left now, -2 times -1 is +2. At -2, -2 times -2 is 4. -3 times -2 is +6. So when I take a look at my graph here, I'm not defined at 0, 0, because in this particular item, this was only when x was less than 0. But at -1, I'm 2. At -2, I'm 4. At -3, we're 6. So we look like a line here. It's off a little bit in my graph. But use line paper, it would have been a little bit easier. So that's that piece of the function. Then the other piece of the function is the square root of x if x is bigger than 0. So let's coordinate this a little bit. So this was -2x when x was less than 0. And over here, we're going to do f of x, and f of x is going to be the square root of x if x is bigger than or equal to 0. So at 0, the square root of 0 is 0. At 1, the square root of 1 is 1. At 4, the square root is 2. At 9, the square root is 3. So we have our square root function here that goes out like so. And because at 0, 0 we are defined, we're going to go ahead and fill that in as far as the bottom function. Okay? So the bottom piece of that function does allow me to go ahead and shade that in. Okay? Maybe if I go ahead and put a point out here a little further, clean this up, so at 4 we would have been at 2. So it looks a little more like that. So hey, there's our first piecewise function. Okay? Also, letter E on this particular item. So to go ahead and find the range. So we previously found the domain. Our range here looks like we go as low as 0, and then we keep going higher. If I take a look at this, I've got an arrow over here that keeps going up, got an arrow over here that keeps going up. So my range then is going to be from 0 out to infinity. Okay? So looks like we have just graphed our first piecewise function. So nice job. How about a second piecewise function here? Now this piecewise function has 3 intervals in it. So we've got 3 pieces where we're defined. So we're going to do the same thing that we did in the last item, except now we have to pay a little closer attention to where we are. So we've got 3 places as far as where we could be. So let's see, f of negative 2. Let's see, negative 2 is going to be in this top region out in here between negative 3 and 1. So that's going to be negative 2 times negative 2 plus 1. So that's 4 plus 1, so that's 5. So f of negative 2 is 5. So I have to figure out, first off, which piece of the function am I using? And in this setup, I was using that top piece. Okay, what's f of 1? So where is 1? So in my regions over here, when x is 1, well, that's kind of easy because I know my middle piece is when x is 1, I have a set function, and it's just 2. It's a constant. So at 1, we're 2. And at 2, what are we? And so over here, when we're 2 is when x is bigger than 1. So since 2 is bigger, then we're going to use the x squared function. So we're going to do the square of 2 in this case, which is 4. So part of this is evaluating the functions. Where in the piecewise function am I referencing? So I have to pay attention over here. What's the x value I want? If I want an x value, say I wanted f of negative 10. F of negative 10 here would be undefined because when I take a look at this, there's no interval in here where I have negative 10. Which leads us then into part B. Let's identify the domain. So if I take a look at the domain of my function, in my function here, I only go as far left as negative 3. Then I go up to 1 less than 1. So I don't use 1, but this middle piece, I do use 1. Then over here, I'm bigger than 1. So I'm going from negative 3 out to infinity. And because this has an or equal sign underneath it, I'm going to use the bracket there. So there's my domain. Okay. Locate any intercepts. Okay. So intercepts, let's see what we can come up with here. So to find an x-intercept, we let y be 0. So I have to say, okay, when y is 0, how about negative 2x plus 1 and 2 and x squared? So this middle piece doesn't make any sense because x cannot be 2. This is a false statement. Okay. How about this first one, though? 0 equals negative 2x plus 1. If I subtract 1 from both sides, we get negative 1 is negative 2x. We'll divide by negative 2. And so we get x is positive 1/2. Now, this negative 2x plus 1 is when we were between x values of negative 3 and 1. Since I am at 1/2, then that is a legitimate item there. So I can have an x-intercept at 1/2 using that definition. At x at 0 equals x squared, if I square root both sides, then x equals 0. However, when I take a look at my function, x equals 0 is this top piece, not the bottom one. So I can't use that because it's not in the domain of that region of the function. So my x-intercept is going to be at 1/2. As a coordinate, that's 1/2, 0. Y-intercepts are much easier because that's when we let x equal 0. So now we want just f of 0. Okay, take a look at our piecewise function here. At 0, when x is 0, that is this top piece. Okay, and then we want negative 2x plus 1. That's when negative 2 times 0 plus 1. That's going to be 0 plus 1, which is 1. So my y-intercept is going to be 0, 1. So y equals 1, or I can say I've got the point 0, 1 as far as in intercept on the y-axis. Okay? So let's see, we found out some different values. We found the domain, we found located the intercepts. Now let's go ahead and do the graph of the function. So if we go ahead and do the graph of the function, we've got three different regions here. We've got when we're between -3 and 1. So 1, 2, 3, 1. So that's going to be, I kind of highlight here, that's going to be one section of the graph. Then I've got at 1. Okay, so at 1, I know that's going to equal 2. So I can plot that directly. And then I'm bigger than 1. So I have another piece here that's going to be out in through there. So if I kind of coordinate this back again, in the top piece, it's going to be that spot. That was just equal to 2. And then I'm going to have that section. So as we go ahead and take a look at -2x plus 1, if I just go ahead and plot some points. Let's plot when we are -3. So let's do x, whoops, let's get our pen tool here again. So I'm doing f of x equals -2x plus 1. So let's use some x and f of x. Let's do a little t-chart here. So I can do -3, and -2, -1, 0, 1, okay? Because those are the integer values that I'm located at. So if I plug -3 in here, I get +6 plus 1 is 7. Plug -2 in here, we get +4 plus 1 is 5. -1 would be 2 plus 1 is 3. At 0, we're 1. No surprise there, because that's what we said our intercept was going to be. And if we were using 1, we have -2 plus 1 would have been 1. So let's see, that means this graph then is kind of working its way down. So at -3, it's 7. So 1, 2, 3, 4, 5, 6, 7. So it'd be way up here. And then at -2, it's going to be -5. -1, it's 3. At 0, it was 1. And then at 1, did I do that backwards here? At 1, -2, it should have been -1. Yeah, something looked off there because it should have been following this same idea here. Okay, so we got a straight line going out that way. And then we're at 1, we're equal to 2. And then beyond 1, we want x squared. So let's see, if I plugged in 1 squared would have been 1, so that would have been here. 2 is 4, so it's 1, 2, 3, 4 is up here. 3 would have been 9, so that's going on farther up there, so it would look like, whoops, took a look at the wrong piece there, would have looked like this. So that is then our piecewise function on example number 4. Now, one thing that we could do, if I would have put grid lines on this and used line paper, that would have looked a fair amount nicer. Okay, but in this case, I didn't use the grid lines, and so we ended up maybe a couple of these points looking like they're off just a little bit. All right, one last example here. Let's do a word problem with piecewise functions. So in the spring of 2018, Duke Energy Progress supplied electricity to residences in South Carolina for a monthly charge of $8.29 plus 8.6035 cents per kilowatt hour for the first 1,000 kilowatt hours supplied in the month, and 9.1446 cents per kilowatt hour for all usage over 1,000 kilowatt hours in the month. So one of the things that we would want to do here is maybe develop, well, what is a piecewise function for this? Okay, so that's going to end up being part C. We're going to develop a model relating the monthly charge in kilowatt hours used. Right, so we're going to express C as a function of X. We're going to see C of X equals, then we're going to end up with something. Before we do that, though, let's answer letter A and letter B. So what's the charge for 500 kilowatt hours in the month? So if we're using 500 kilowatt hours, we get charged a charge of $8.29 plus, and it's either 8 cents for the first 1,000 or 9 cents for everything over 1,000. And so in our case, since we're at 500, we're under that first 1,000, which means 8.6035 cents for that. So our charge then is going to end up being, well, we got our $8.29 plus. Now, this is a little interesting here. We have 8.6035 cents. Notice our units changed, went from dollars to the cent sign. So in dollars, This cents would be 0.08. That'd be 8 cents. Then just carry the other values behind that. So that would be the dollar amount. So we want plus 500 kilowatts. So 500 times that value, because it's 500 and kilowatt hours, and every kilowatt hour is going to be 0.086035 as far as my charge. So on this one, this ends up being a calculator activity. So I say maybe my cost equals, so I plug that into my calculator. If I round it to the closest penny, because that's how we get charged for anything, we get charged to the closest penny in the sense that when I pay somebody, I can only go down to the closest cent. So on part A, I've got $51.31. That would be my cost for the month. Let's do part B. Let's say now we use $1,500 per kilowatt hour. Okay? So when we take a look at the setup here, let me erase some of this stuff up in through here. My charge is going to end up being $8.29. Okay, so I get that automatically no matter what. So my cost is going to be $8.29. And then I get basically 8 cents for the first 1,000 kilowatt hours. So I've got 1,500. So I really have, in this case, I've got 1,000. So I've got those 1,000 hours plus another 500. So this first 1,000 gets charged at 8.6 cents, and the next 500 get charged at the 9-cent charge. So I'm going to end up with 1,000 getting charged at the 0.086035, and then my next 500 are going to get charged at a rate of 0.091446. Okay. So my 1,500 totals, there's the first 1,000, there's the next 500. So here, that would be the cost for 1,000, this would be the cost for 500, added to my monthly charge anyway, just for having the electricity turned on, it's going to be $8.29. So what we do then, we just plug this into the calculator, and we see, well, what do we end up with? So I've already calculated this, and I ended up with $140.05. So let's take a look at letter C then. Let's develop our piecewise function. So C in terms of x. So what we have overall, we've got two scenarios. So we're going to have something, let's do it this way, move this out a little bit. When our cost, when x is between 0 and 1,000, and then we have a charge when x is more than 1,000 as far as kilowatt hours. So I'm going to end up with 829 plus, let's see, what was it? It was going to be this amount here, 0.086035x, okay, for every, and if x is a kilowatt hours, for every kilowatt hour between 0 and 1,000. Then I'm going to get charged 829 plus 0.086035 times 1,000. So I'm going to have that first 1,000. Plus then I'm going to end up with, let's see, I'm going to have the dollar amount, 0.09, what do we have here? So this amount here, 0.091446 for anything over 1,000. So if I'm over 1,000, well, how far over 1,000 are we? Well, what we'd have to do then is we'd have to take our kilowatt hours and then subtract 1,000. That'll tell me how far beyond I am. So this would be if we have a charge that's greater than 1,000. So that would be our piecewise function. Now, one of the things that we would like to do on something of this sort is to clean this up a little bit, because that we can go ahead and add together. We can calculate that. So I would go ahead and revise this and say this is 8.29 plus the 0.086035x when our kilowatt hours is between 0 and 1,000. Then if I multiply and add those together, that ends up being $94.33 plus then this other part. Whoops, not completely. If I go ahead and distribute this, if I distribute that and then combine like terms, I end up with $94.33 plus that 0.091446 um, x. Okay, and that would be when x is bigger than 1,000. So that would be my cost in terms of x, this final item down through here. So I went through that rather quickly. Let me go ahead and come back and just make sure it makes sense. So this part here, okay, I would have had 829 plus, and if I multiply by 1,000, 1, 2, 3, plus $86, oops, 86.035, plus then 0.091446x minus, if I multiply the 0.091446 by 1,000, that would have moved the decimal over and made it $91.44.6. If I combine these values here, that's where I'm getting the 94.33. So we could plug that in the calculator, identify what those items are, and that would be our end result. So our piecewise function here looks a little bit cleaner because I have that part and then that part. All right, so a lot of stuff today in today's video. So we looked at the library of functions, okay, which are these 9 functions down here. Functions that we should have a basic understanding with overall. And then we took a look at the piecewise functions. The piecewise functions were the functions that are defined in pieces, so they have different parts to them. Okay, all right, so hopefully you understand a lot of that material. Again, if, like in all the other videos, if you notice that there's been a mistake made, please go ahead and drop me a line, let me know. Otherwise, that is Chapter 3, Section 4, and I will see you back again, hopefully, in Chapter 3, Section 5.